collision problems might sound difficult, but they're really not all that difficult if you remember the conservation of momentum. So if you can recall, the conservation momentum states that the sum of the initial momentums equals the sum of the final momentums. And so let's say we have two objects, okay, and it doesn't matter what direction they're going, it doesn't matter what the mass is, okay? So we have two objects that are going to strike each other. Initially, we would have mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial. And then those would just equal our mass 1 times its final velocity plus mass 2 times its final velocity. And then we have our vectors here. And then it's a pretty simple, straightforward problem. Okay? We'd have to be given 3 of the unknowns, basically, right? We'd have to be given mass 1, mass 2, and VI, or actually more than 3. We need more than 3 to solve this problem, okay? But we'd be either looking for the initial velocities or the final velocity of something, or even maybe what are the masses. All right, so let's say that we have two objects, mass 1, mass 2. And this is going to be an elastic collision. If you recall, in an elastic collision, you have both momentum and kinetic energy conserved. Okay? So sometimes that could lead to some problems, and some people want to use the kinetic energy equation, and technically you can. The problem is when you're just making up random numbers to put in, you're not exactly sure if both are going to work out. That might be a little hard to understand. So a lot of times in class, instead of talking about elastic collisions, we will just call it an inelastic collision. Because an inelastic collision, you only have conservation of momentum. Right? So we're going to give mass 1 a mass of 2.0 kilograms. We'll say mass 2 is 10.0 kilograms. We'll say the initial velocity V1, it's going to be hard to read that, V1I is going to be equal to positive 5.0 meters per second. And we'll say the velocity of 2 initially is negative 3.0 meters per second. Now you'll notice I have the vector signs, and it's important to have a plus and a minus based on its direction. You can see here we're going to the right, and so 1 would be positive. And over here we're moving to the left, so 2 would be the negative. Now, we need something else. Okay? Let's say, I'm not sure if you're going to be able to tell the colors here, but let's say that mass 1 bounces backwards. I mean, if you think about it, it might, okay? Mass 2 is very, very large, and it's moving at a similar velocity, okay, to mass 1. Let's say it bounces back with a final velocity of negative 7.0 meters per second. So ultimately, what are we trying to find? The final velocity of the second ball. You know, the final velocity could be this way, it could be this way, and we're going to rely on our sign to actually give us that answer. All right? So our conservation momentum problem or equation is here, and all we have to do now is plug those numbers in. I am going to run out of room, so I'm actually not going to write the units. Just be careful. Remember that conservation of momentum, and momentum has the units of kg meters per second, so kilograms meter per second. All right. So my mass 1, 2.0 times, right here, V1I plus 5 Now we have mass 2, which is 10, times the initial velocity, -3, equals, and I'm going to write on the bottom here, mass 1, 2.0, times the final velocity. Right? And then over here we have plus mass 2, which we know is 10, times V2F, which is what we're looking for. A lot of times students will work through this and they'll put all the numbers in like I did here. Personally, when I solve for it, I like to leave it all as the variables. So what I'm going to do is I'm going to solve it here, and then I'm going to go back and I'm going to rewrite it with just the variables so you can see how that works. All right? So 2 times 5 is 10 minus 30. Right? 10 minus 30 would be -20 is equal to 2 times -7, 14, okay, plus 10. I'm going to work this out. I'm going to add 14 to each side. There's a little brain hiccup there. I forgot. 6, and then be divided by 10. All right. And so our final velocity is going to be equal to negative, now what is that? What's 6 over 10? 0.6. If I look at my significant figures, we should have 2. And that would be in meters per second. So mass 2 actually hits and almost stops. It doesn't move too fast at all, but it does slightly move in this direction. Right? It's not too hard to do these problems because that's all they look like as far as the equation goes. Right. We're going to erase this. So how about if I was not going to put the numbers in and I'm going to solve for this, V2F? What do? First things first, I'm going to take this and I'm going to take it to the other side. That would get all of our like terms on one side. All right, and then I'll divide by M2. All right, and that would be the expression. Once again, you plug all the numbers in and you get the same exact answer.